Okay, good morning. So in the last class, we have deduced this Young's inequality starting from a function and using the calculus, one variable calculus, using the maxima minima that you have learned. And I also left out an exercise. So in this case, we have also so fill this. So when this will be equality. So we have also looked at this equality. This inequality becomes a equality when x power p is same as y power q. And I would request you to find out all other things. There are a number of other equalities. If you take the qth root of this, then maybe x power 1 by q should be y power 1 by p. That's also another equivalent statement. So this is what we looked at. And in the last class, I also asked you to look at the following graph. How many of you could get that if f is a function increasing and f at 0 is 0? So I'm considering only the positive side of it. Okay, so I asked if you give an increasing function. Then what is this? Is if this is CF, how do you understand G? How many of you could get that? Inverse function. So in the discussion place, I have looked at some of you could figure it out. Say for example, if the function is x square, then this inverse is square root of x. Okay, so that kind of inverse. And is there any way to understand the same thing in the graph? Many of you could achieve that if you flip this with respect to y equal to x line, that will be the graph. Or in other words, just be with me in understanding. This is my picture. So if I look at from this side, so if I look at from this side, and can you see that this is the graph of the function? So thinking that this is the axis, base axis, this will be the function of g. How many of you agree? Only three. Whatever you said is right. So if I keep imaginary line y equal to x line, so this y equal to x line, if I keep it, then if I rotate this, that means this line will become x-axis and this line will be y-axis. But if you from there, if you look at the picture, will be the way that you are looking from this side, from this side. If you are agreeing on that, then we can go ahead. Okay. So, okay. So many of you could not get convinced then again I would suggest you to spend time in understanding that. Okay, only 10 people. What I want you to look at is the following. This is something familiar. Once you understand this, then this will be familiar to you. So I consider a. Okay. So I integrate this function f from 0 to a. And so this area, can you see that it is nothing but integration of fx dx from 0 to a? I hope this you will agree. Yes? Good. So this is something familiar to you. And the way I said, now suppose if I consider a b here. So consider a b here. And now I'm just going to write something and see that whether you're able to make sense. So this part. Can you convince that this is nothing but integration of this g? See, this is the fx dx, x and t are all kind of dummy variable. Do you accept this? In those who understood, this is the g. What is the connection between f and g? F of g of x is x. Same way g of f of x is also x. So g is the inverse under the composition. Good. So if you understood this part, then it is immediate. Now I want you to look at so I look at the following, at integral of f t dt 0 to a plus integral of f t dt 0 to b. And can you comment something about this a into b? So what is a into b? It is the rectangle whose length and breadth are a and b. So can you see this? So this is the area that we are considering. Yeah. So if you think what is the connection between in terms of inequality? If you think it is greater than or equal to, then say yes. Otherwise, so say no. Good. So I take it granted that so this inequality is clear at least from this picture. Okay. Thank you. Good. Now this is for this particular b. What if I take the b to be smaller? So let me do that also. What if I take this b to be smaller? Say this. This is my b now. Suppose this is my b. That means we look at only this area. Now is this inequality still true? So the previous inequality reason is that this portion is not covered. But if I take B to be like this, can you see that A into B will be this? So this portion will not be counted. So is it clear? Okay. So convince yourself that it doesn't matter wherever you take B, there is some portion that we are actually leaving out. So this green plus blue, this part is not included into A into B. Yes. So there is still AB is smaller. And hence, so this is true for any B. And can you, so those who could get immediately the answer can say yes, that when this will be actually equality. Yeah, Himanshu? Oh, many people.
Sir, when A will be equal to B.
A equal to B? Yeah, Srujana?
When A comma B lies on the graph.
Okay, so when A comma B. What is the meaning?
F of A equal to B.
Yeah, so it is Himanshu, it's clear?
Yes, sir. Actually,
Yeah, that's okay. So note that the equality happens when f of A is B. So that's where this happens. So at this point, if I consider, then it will be the same for both. Okay. So what is this inequality has to do with? So here comes quick. So keep pen and paper with you. All of you have some paper and pen with you? Okay. Grab a pen and paper because this class I want your calculation skills with me. Right. So all that we are saying now is that the equality happens. So when f of A is actually equal to B. Okay. Now here comes the specific case that I want to look at. See, the reason for deducing this geometric inequality is that other way of deducing the Young's inequality from this. And can you compare and see that what kind of function I should consider to get Young's inequality? That's obvious, right? So you have some function, and if you integrate, you should get this kind of, this left hand side is something like A and B. I call it as X and Y here, that's fine. But other side, if I want to get X power P by P, then what kind of function I should start with is also clear. So start with, so let f of x equal to x to the power P minus 1. I hope you all would have guessed correctly. But remember, this whole condition is based on certain assumptions. That is, so f is increasing. Okay, then only you can actually find out. It should be 1, 1 and on 2 to find out the inverse, right? And f at 0 is also 0. That's how the graph was saying. And of course, continuity is also assumed in this case. Of course, integrable at least. So nothing wrong in even considering f is continuous. So this is the assumption that we have. So does this function satisfy all this? The function x to the power P minus 1. At 0, its value is clear. Check. Okay, so this satisfies that. And if I substitute, so what is the inverse function? What will be g of x? Ritesh?
Sir, x to power 1 by p minus 1.
Yeah.
A root of p minus.
Yes, yes. That's it. Okay, so now substitute this and then tell me, are you getting it? So I'll give you a couple of minutes for you to check. And if you, without even writing, if you could see that, that's also fine. So work out either in paper or if you can do it in mind, it's also fine. So first one is clear. If I take the integration, it becomes x power p minus 1 plus 1 divided by that p minus 1 plus 1. So it is x power p by p. That's fine. And 0 to a. So at a is a first, I will get a power p by p. That part is done. Second part I need to find out. So integration becomes x to the power 1 by p minus 1 plus 1. And the same factor in the denominator. So all that you need to observe. So I'll finally ask the following question. What is p by p minus 1? So this you are using. So use this fact to control. Right. So 10 of you got it. I don't know what about others. Okay. So do it at least once. So that proves, so by substituting this, so then we get ends. And check that the equality also similarly reflecting that. So in this case, if this happens, we have already said that the equality happens when f of a equal to b. That means you can check that whenever x power p minus 1 or a power p minus 1 should be equal to b, or x power p minus 1 should be equal to y, and check that the same condition is reflected again in terms of the inequality. So here the question is, is it same as saying x power p minus 1 is equal to y? Okay. Verify. It's not even exercise, you have to check. Right. Okay, so we are going ahead. Is there any doubt as of now? Good. Okay, so using this, see, our purpose is to create some kind of inequalities, because every time we have to check the triangle inequality. So this whole discussion for the last part of the last lecture and this whole lecture, we are dealing with this inequalities because it runs for a longer time. So we don't need to do every time a new tool. So the holistic tools we are looking at. So the next thing that I want to, the next important result in this kind of inequality is what is called Hölder's inequality. Sometimes so what it says is the following. Now I will, before going into this Hölder's inequality, let us write certain definitions. For example, Now I want to define using this. So for an element in Rn, there are some norms that we have defined. So we want to define such a norm with respect to this p. So what is p? P is between 0 and 1 and infinity. And this norm is defined as this whole power 1 by p. Okay. So this is what is called p now. Check that this definition works out with whatever already we have learned, even for 1. Even if I consider 1, it is summation of the mod xi. That's what we call it as 1. And for infinity norm, as we have already looked at, it is maximum of these x's. So this is an infinite. So in fact, this definition we can consider. Now for this, Hölder's inequality says the following. If I consider x and y from Rn, then if I consider summation xi yi, okay, I equal to 1 to n. This is actually less than or equal to norm of xp into norm of yk. So if you can actually correctly interpret what does it mean, it is in some sense you take x coordinate, x vector in Rn which has n coordinates, and y vector with the n coordinates, and coordinate wise you are multiplying. So it is in some sense this xy vector point wise, coordinate wise multiplication. For that I am finding the 1 now. Is it clear? This is a kind of notation right now. Okay, so this is the inequality that we want to first establish. From this follows from the Young's inequality with appropriate choice of thing. Can you suggest? So look at the Young's inequality. So what I should, what kind of substitution I should do, or what kind of x and y I should take and use the Young's inequality, and then I will get Hölder's inequality. So that immediately suggests that maybe I will use it for xi and yi. Each coordinate I will use. Then I get xi yi, which is less than or equal to xi power p by p plus yi power q by q. And then I will take the summation. That will be the first impulse. But if I do it that, can you see that it becomes summation of xi power p by p plus summation yi power q by q. So there is no way that I can combine and take things to make it easy. So look at this expression. Wherever all it says is that somewhere if I use, look at the Hölder's inequality, what we are saying, there is no 1 by p term or q terms are appearing here unless in the norm, okay, in this kind of definition. Remember, so far, though I have defined this xp norm and x infinity, I call it as p norm, we are yet to say that it is actually norm. So we have not proved the triangle inequality. Keep that in mind. So this is just some expression, some function as of now. Right. So it suggests that directly taking only xi's and yi's in the triangle inequality will not work out. So I will take what you regularly do is called normalized. So I take xi divided by norm of xp. What is this by definition? It is not xi divided by summation xi power p whole power 1 by p. Okay. And similarly yi power, this is what I'm taking. So I'll call this is my Young's inequality with the x as this as my, so this as my a, and this is my b. So look at the final expression here. So in this, no, sorry, the Young's inequality. Okay, so I'm substituting this in the Young's inequality, and can you see that this will give me the following, that is xi power p, because this is one term, it's like a. So a power p, that means this power p divided by p, so I'm writing it here, plus, and this is the b term, so that power p, that is yi power q into norm y, this power q into 1 by q. Now this is, I do it for each n, and I then take the summation. Okay, so what do I get? It is summation xi yi divided by norm x power p norm y power q, and this will become less than or equal to, taking the summation. Remember, the numerator p are all common for all the things. Only change is in the numerator, which is in terms of I. I'm doing the summation over I. So what do I get? Is 1 by p summation or p and this also comes out with norm x p power p, and then this you will get it as norm of xi power p. Similarly, 1 by q times norm x q power q, and this is norm x norm yi power q. Okay. Now can you identify what is this? So identify this is nothing but the pth root of norm x. See, if this whole power 1 by p, if it is there, that's what we call it as norm x p, norm x suffix p. But this is without that power 1 by p, and so it is norm x power p. So that will cancel with this. So I have only on the right hand side only 1 by p plus 1 by q, which I know it is 1, and push this. So this whole thing is less than or equal to 1. And now these are all independent of the index summation I. So I can take it to the other side and I will get the required Hölder's inequality. So take a couple of minutes to understand. And if you got this, I'm clearing it out. If you got this, then say yes. Good. Now I want to add the following questions. So this whole inequality is coming from the Young's inequality, and hence it is true for this, because the Young's inequality we have established for p bigger than 1 and p less than infinity. But I'm little curious to ask the question, does the inequality remains to be true for p equal to 1 also? What's your answer? Which means on the right hand side it will be 1 norm of x. If p is equal to 1, what will be q? Q is infinity. Okay, that's the convention we are taking now. So can I replace the right hand side with 1 norm of x and infinity norm of y? So all that you need to observe is the following: the modulus of xi into yi is less than or equal to mod xi into mod yi, but mod yi is less than or equal to infinity norm of y. So everywhere you can replace this by mod norm y infinity norm of y, and that's common, so you can push out. What remains is only summation mod xi. So here is the exercise. check that this is also true for. So I can write this to be 1 infinity. That means p equal to 1 and q equal to infinity. Or you can change the roles of x and y also. Okay. So using this Hölder's inequality, we can go ahead and prove another important inequality which appears number of times, is what is known as Minkowski's inequality. So what is this Minkowski inequality? It says the following, that if I consider, since with the assumption of so with this definition, keep this definition in mind. So with respect to this p norm infinity norm definition, all it says is if I take x plus y. See, remember this is a valid object in Rn. Okay. And this is, if I take any p, this is so it's about the same p. There is no change on the. Which means what we need to prove is that if I start with summation of xi plus yi power p whole power 1 by p is less than or equal to summation xi power p summation yi power p whole power. So this is what the inequality actually says. So the way to, again, these are all long-standing good inequalities. There is some kind of trick, okay, to get this. The trick is not very difficult. All you need to start with is that I want to use the Hölder's inequality. Somehow I need to understand this, the left-hand side, as a product of two things. Remember, the Hölder's inequality says that if I multiply xi into yi, then I can split. But in terms of product. But here it is saying actually in terms of addition. So start with the following. Maybe I'll write here. So start with only this part. So start with P. All that you need to do is this, you try to write it as split into two parts. That is some 1 for p minus 1 and 1. Okay. So now it is something like this is one term. So this is like one term. And this is like another term. Or 1. Now apply the Hölder's inequality and you will get the Minkowski inequality. Maybe. So all that I do is that from here I can write this is less than or equal to. For want of space I am writing here. So this is same as for p minus 1. And this I can write with the inequality that I will write as mod xi. I am using the triangle inequality of real numbers. This I can do. And which I can actually write it split into parts. What I mean by that is this. After writing this, I can actually write this. You agree? This part? I have used the triangle inequality to split this, and then I wrote it like this. Okay. Now I use the Hölder's inequality for this. Can you tell me what do you get in this case? So this is like xi and this is like yi. So two terms. Consider a and b. So it is a power p and this power q. So maybe you can change the roles and then write the mod xi in the front if you want, and then take it to the power. So I write this as this is mod xi power p. Or in other words, what is the precise Hölder's inequality I can use? Can you see that it is summation mod xp? Okay, this terms mod p, and this elements mod q, q norm of that. So which is this. Power q power 1 by q. So the next term also we'll write accordingly. And can you simplify this? Can you see that it is p minus 1 into q, which is pq minus q, and for which I know that it is p. So it becomes norm x power p, and this is over p, but outside it is actually 1 by q. And see that you get this similar expression on the other side also, which will be norm y p plus the same term. Now take that term common, and what you get is okay. But what is the left hand side? Look at this is the one. Okay, so this is the same expression. This is also same expression, but this side the power is actually 1. Other side the power is 1 by p. So if I take this is a product of now. If you take it to the other side, it becomes 1 by 1 minus 1 by p, which turn out by q. So it is 1 by q. So 1 minus 1 by q, you will get p. So take this to the other side. And so what you end up is this power p whole power 1 minus 1 by q, which is less than or equal to but 1 minus 1 by q I can replace and write it as 1 by t, and that's nothing but norm of x plus y power p norm of this. So take a couple of minutes to go through and see that are you able to get what you want. Once you get that, then say yes. So all you need to actually remember to get Minkowski inequality. So we could derive the Minkowski's inequality from Hölder's inequality. The only thing that you need to use is that given a term, you split into two parts. So this will be a recurring theme in many places again. It's again another kind of mathematical tool. So all that this whole proof, if you remember only this part, so the crucial part is only this much. Splitting. Only this splitting, if you remember, then apply the triangle inequality for the simpler part, and then you go ahead with appropriate powers. Now, you can also end up saying that if I take this part, there could be a confusion in terms of if I take the power of p, then it will be a problem. So identify there itself. For this, I will apply power q, and for the xi, I will apply power p, so that I will get whatever. So that the remaining things are just simple calculation. But here again, I want to ask the following question. So this whole inequality is coming from the holders. So this is true. At least this part is immediate. Is it also true for p equal to 1? Check that the powers are dropped. It is just splitting mod xi plus yi. You have to split into two parts and then rewrite them. Okay. So this is also true for this. Again, I will. So this is true for this. What about p equal to infinity? Equal to infinity, the definition is maximum of the xi plus yi. That should be less than or equal to. That we have already verified. Okay, so both the things again. So this is also true. So check p equal to 1 infinity. Okay, both of this we have already done in it. And so the Minkowski inequality is true for including even the end 1 and infinity. And here comes the question that I leave it. Namachiva, I'm asked some question that check that why we are considering only p bigger than or equal to 1. It was all the proofs, but you can check whether the inequality is true for p whose value is less than 1. So we get the whole triangle Minkowski inequality. Can you see that this is the triangle inequality for the p now? Yes. So this is actually the triangle inequality for p now. And the triangle inequality of the scalar multiple is easy for the p now. Scalar multiple is easy to check. Non-negativity is also easy to check. And triangle inequality for the p norm is established by the Minkowski's inequality. And hence, all that gives you is the following. So in Rn, we can actually define p norm, or in fact kn also, since we are using modulus. For all p, this is a nonlinear space. So these are all number of nonlinear spaces. Remember, p could be anything between 1 and infinity, and don't always think that p's are only integers. P could be root 2 also. So we got at least infinitely many nonlinear spaces on the same space. So on the same vector space, you can define infinitely many nonlinears, infinitely many different norms. And again, you can go back now and check that if I take n equal to 1 case, what happens to all these p norms? It should coincide with your modulus, because we have already proved in k there's only one norm which is modulus. So check sure that this is the only norm, excluding the scalar multiplication. Okay. Now let's go ahead. So using this, we can also get the following things. I'm going to write something. I can define the same XP now. In the infinite case, that is, I'm defining something. So it is xi power p, but the summation is now 1 to infinity. Okay, so this is whenever defined. So for all xi's, this may not be a valid object, but whenever I can define this, I define this xp, and I want to ask the following question: that is the Minkowski true? Is the Minkowski inequality true in this case? That is norm of x plus remember, for finite things we could do. Now how do we do the infinite? Again, this is what I would like you to please re-emphasize, that for, so this fact I want you to keep. So for any natural number n, is this true?
వేసుకున్నానమ్మా టానిక్ తగిన ముందు నీళ్ళు ఇవన్నీ వచ్చిందా నీళ్ళు కూడా
Do you all agree this? For any natural number, this is true. From the Minkowski inequality for Rn. For any n, it is true as such. And now from here, I'm saying that from this we can get the Minkowski inequality, even if the elements are not from Rn. In fact, from a sequence. Look at that. This is a axis, actually sequence. So this axis sequence. Whenever it makes sense. And how do we get this? Again, I quickly say that, but please discuss and then make sure you are understanding that part. That this is, look at each of this part. This is nothing but the tail of, this is the partial sum, 1 to n. So this is the partial sum of this series. This is the partial sum of this. And these are series with non-negative terms. And hence it is increasing. So if you have a sequence which is increasing, these partial sums are increasing because it's you are adding terms. So it is an increasing sequence of positive terms which are actually bounded by this expression. Because you know this definition that in the case of increasing sequence, the partial sum has to converge to its least upper bound. So the least upper bound is this, and hence this will converge to norm of xp, and this will also converge to norm of yp. Or in other words, this is a partial sum which has to be less than or equal to least upper bound, and this also has to be less than or equal to the least upper bound. And so first you will apply this and then conclude that this is less than or equal to. First you conclude this, and now for every n this inequality is true. That means this right hand side. So this right hand side is an upper bound for these kind of sums. And these are partial sums. Again, it is increasing. So you have an increasing sequence which is bounded above, and hence it has to converge. But I know that for increasing sequence, the limit is the least upper bound, and hence you will get this. So make sure that you are understanding this in the appropriate. If you take the left hand side first, then you will not get what you want. So it is passing through the partial sums, we could actually conclude this. And I leave it for you to check is the same thing works for holders. Similar argument for the product also, can you do that? Again, it's through the partial sums. And now, once we have created this inequality for even sequences, whenever defined, that gives you a nice and natural notion of defining the new objects. Like as we have already defined something called L1 and L infinity, now we can actually define LP, which is nothing but set of all sequences AN, such that this P now, okay. This you want it to be finite. But notice that once the series, the inside term bracket, if it is a finite term, the pth root also will be there. So books may not write this, so they may just avoid this and write only this much. Can you see both of them are same, this definition? So LP is the space of all sequences, which we call it as P summable. So it is P summable. And hence now for all values of P between 1 to infinity, you can define this space. And now if I want to first check, is it a vector space? How do I define the addition is clear. How do I multiply the scalar multiplication is also clear. But if I take the addition, what guarantees that if AN is in LP and BN is in LP, why AN plus BN has to be in LP? So if I have Xn is in LP and Yn is in LP, or X and Y are in LP, what guarantees that X plus Y also has to be there? That precisely guaranteed by Minkowski inequality. So the Minkowski inequality actually tells you that this is a vector space. And it does the other thing also. So on this ELP, we can very well define this P now. So take a couple of minutes to check that what are the properties that you are using to say that it is actually a vector space, as well as this P norm is actually a norm. This is defined for all, now including the L1 and L2, which we have already defined. This has created this much of spaces. Is it clear that to prove the triangle inequality, you need the Minkowski inequality? To say that this norm is satisfying the triangle inequality, you know Minkowski. But even before that, saying that the LP is a vector space, you need triangle inequality. That Minkowski inequality is giving you that conclusion. Now here comes another exercise for the weekend. We have defined spaces called C0 naught is a space of all sequences except few terms, finitely many terms, remaining all terms are zero. Means after stage n, all elements of the sequences are zero. C0 is all those sequences which are converging to zero. I'll also include another space which is C, which is set of all converging sequences. And the C naught is the sequences which are converging to 0. This can converge to anything. It can converge to 1 also. And now you have all these LP spaces. Or maybe I'll write L1, L infinity, and L2. Now, the exercise is try to see the connection among the spaces. So what do I mean by that? Which is a bigger space, which is a smaller space, and in which space you can define which norm. And okay, if it is a something is a subset of the other one, then that norm also can be defined. But there is also another norm here, so you can look at this, all this. And the second exercise is that which I would expect you to do every time. That think of some elements, okay? Elements in each space. And you can also ask the question that suppose the way we did C naught naught is contained in say C naught, but there are elements in C naught which are not in C naught naught. So you can look for that kind of elements in each space and some kind of exclusion, special elements. And third, this I want you to surely make sure that look for elements whose norm are 1. Are vectors of length 1. Okay. So don't just start with just creating only one element. Try to look up what are the general properties of these kind of elements. So if you have any questions, you can ask, and I have a small poll for you, and then if you have any doubt, you can ask. Otherwise, there is a small poll that I will launch that you can answer, and then we'll wind up with this class. Okay. Then I'm launching the poll. I'll stop sharing.